Hello and welcome back to Calculus 2. This is the last section in chapter 10. We are talking about ways to check for convergence, divergence. We know there are 10 tests. The burning question is, which one do I use when I see a series? Now, if you go online, and I should have pulled this before, you will see, let me just go infinite series. Infinite series. Oh, there it is. So if you are if you are good with algorithms, then you're going to take a look at something like this and understand it. Yeah, good luck with this. So what you have here is a flow chart of the ways to think about series. If you have a problem, look like this, do this, right? Use this test, use that test, converge, divergence, so on. So it's not a bad idea to look at this. If it's making you go crazy and confused, then abandon the ship, obviously, and rewatch this video, I guess. But if a flow chart, and I just Googled this, I typed in the Google search, I just went and said infinite series tests, and then just went to images, and eventually this one popped up. You will find it by these green and red boxes on the side. So it gives you like a flow chart of what you should do. And the most important thing here is the divergence test. So this is where everything begins. Divergence test is simply you take the limit of the sequence within the series, and if that one gives you something different than 0, it diverges and you're done, right? So you should always start there. Just like I always told you before, I always start with the u sub. Can I use u sub to solve this integral, right? Well, now it's divergence test. Can I use divergence test? And if you get 0, then you have to take a look at other 9 tests. But if you get something other than 0, it diverges by the divergence test, and you're done. The problem is solved in literally 15 seconds. So when you are talking about choosing a test, number 1 here in red, in blood, use divergence test first. So if the limit of an is equal to 0, use other test. But if limit n goes to infinity of an is different than 0, then diverges. The series an diverges and you are done. So that's number 1. When you look at your exam, let's say you have the worst possible exam is just 10 problems, 10 series, no wording whatsoever. The directions on the test say test for convergence. And then you just have 1 through 10. There is no other words on the entire exam. The first thing you do on the test like that, or any test, is you apply divergence test to each one. 1 or 2 of them might have the limit to be different than 0, and those are divergent right away, and then you get to focus on other problems. So in some cases, guys, this divergence test might knock out the problem in 15 seconds, and you're done. So now, if divergence test is, if you get equal to 0, then you have to use one of the other 9 tests. So here are those other ones. Number 2, ask yourself, is it geometric? Meaning, does it have the form of AR to the n? Because anything that is exponential, you have 3 to the n, 1/2 to the n, e to the n, right? Whatever you have of these, they're all geometric. And then you just look at the value for r. If it's bigger than 3, if it's bigger than 1, like 3 and e, it's divergent. If it's less than 1, like 1/2, it's convergent. So you know that the geometric series looks like exponential function, and you just need to look at r, and you are done immediately. So that's a very quick problem to spot and do instantly. Number 3, another extremely cheap and easy one is p-series. Is it p-series? So, which is summation of 1 over n to the p. So is it that one? Because if it is, let's say you have, well, all of these should have summations in front, but whatever. Let's say you have a summation of 1 over n to the 5, summation of n to the 6, summation of 3 over n, right? All of these are p-series. These 3 gets kicked in front of the summation symbol, and you just have 1 over n. You know, it diverges. It's harmonic, right? Because n is equal to 1. And then you just look if the p is bigger than 1 or p is less than equal than 1. There is a convergence, there is a divergence, and you are done instantly. So you take your exam, you write your name, and then you apply divergence test, the nth term test, which is the first row on your sheet. You apply that to every single problem. When you are done with that, you go to the next problem and you say, is this geometric? No. Is it p-series? No. Then you have the next question, which I always ask myself, is it a mix of different functions? Because that implies ratio, right? Mix of different functions. Is there n factorial? Because all is there n factorial? Because in that case, it's a ratio test. Number 5 is the an raised to the n, because in that case, it's a root test. It's you know, when you categorize this in your head, it's fairly simple to figure out. Number 6. Does it have -1 to the n? Because in that case, it's alternating series test, right? So it's every single one has something that you guys can exploit to do the problem, right? Now, the tough ones to spot, well, telescoping is easy to spot if you have an plus 1 minus an, sure. But remember that some of those problems ask you to do partial fraction decomposition, right? So telescoping series doesn't need to be, oh, this is cheap and easy, just go. Hard ones to spot could be telescoping series, integral test, and obviously both of the comparison limit and direct comparison. So those are the tricky ones. The rest of the tests are all plain vanilla. They all have a feature that stands out instantly, and if you study it for longer than 25 minutes, you will know how to do those 6 tests instantly. But those 4 at the end, those are the biggies, right? So again, apply divergence everywhere, and then you are looking for special features to get into the geometric p-series, to get into root and ratio, which are the one, and the alternating. So right off the bat, you should be able to do 60% because I labeled those as obvious. If you studied and you understand this on any level, those 6 should be obvious. Now the hard ones. Integral test. Well, we need to be able to integrate the function. Remember how we had summation of 1 over n times ln n squared? You remember that one? That was a nice u sub, so that helps, right? You need to be able. And also in blood, must show all 3 conditions. Now, for most of the part in the past, I generally specify use integral test to show divergence or convergence of this series, and then series right there, right? So now you know that you don't have to shovel through the rest of them. You just have to apply integral test, but then integral test is, right, proof number 1, proof number 2, it's continuous, decreasing, positive, those 3, and then improper integral, and then the conclusion at the end that says that they both converge or both diverge. So integral test is the tough one. Number 8, very rare on exams, telescoping series. Now telescoping, they have the easy one. If you have summation of an plus 1 or something minus an, so that's the easy to spot. You see the subtraction, you know it's telescoping, you go the cases and so on. Hard one is when you have to use partial fraction decomposition. Use partial fraction decomposition to convert series into telescoping. Now I'm going to jump to a lecture when we had this at 10.3 and go down to telescoping series and say, look at the first problem. Oh, really cool, right? We have subtraction of the 2, obviously telescoping. Moving to the next problem, we have subtraction of the 2, obviously telescoping, right? Woohoo. And now, here it is. That is not a sequence minus a sequence, right? It doesn't look like telescoping. But then through use of partial fraction decomposition, which is the procedure you know from the previous exam for integrals, we transformed the problem into telescoping and then do the cases, subtraction, and all that. So that's the part where telescoping can be tricky if you have to convert. So factor, do the partial fraction decomposition, and then deal with the rest. So that's that part. And then finally, at the end over here, number 9/10, last resort. So 9/10, last resort. Comparison tests. 95% of problems. Limit. Comparison. 5% of problems. Direct comparison. Is this really 95 and 5? No. Right? But I just had to put some array. So that's the list. And if you want a more comprehensive list, you will look at that file that I showed you on, just Google it, infinite series tests, type that in Google, go to pictures and find the one with those red and green boxes. And it's a flow chart of, now obviously you can Google also the flow chart of series and a whole bunch of different things that you guys can type in to come up with the answer. And that takes care of the choosing the test. So now the skill, right? Obviously, doing a whole bunch of problems will get you to quickly figure out which test is the appropriate test to be used. Now, since you all have access to the book, either you have the book or you have the access to the book in the MyMathLab, you can all get to this page whether you have the physical copy or not. If you don't have the physical copy, right, then you have to figure out where to get these problems, because we are not solving any problems now, because mechanics of solving these problems are all in the previous lectures that we had. We are talking solely about which method is to be used. So when I read problem 17, we're going to take a look at 17 and we're just going to figure out which method. Now, doing the footwork is your practice at home, because that's not what is the part of this lecture. So I'm going to increase the font over here so we can all see, and then jump into these group of problems 11 through 22 and talk about these. So what page we are on? 703. So page 703 in our textbook, and we are going to take a look at few of these problems. So now pick any problem, doesn't matter. Pick one.
16.
Problem 16. Excellent. Problem 16, I'll write it. It goes from 1 to infinity, 7 to the k, I'll put 7 to the n factorial plus 10. The first order of business is to try our divergence test, the nth term test. We take the limit of an, which is all of this, and we have the faster growing function in denominator, because factorials grow faster than exponentials. Therefore, the limit is 0. Test is inconclusive, so it did not diverge by the divergence test. Therefore, we have to use something else. Now, what is the feature that you guys would, from what I talked about earlier, what would be the feature to immediately spot in problem 16 to know which test we have to use? Factorial. You see a factorial, immediately screams ratio test, right? Ratio test. Now, it is good for you to go to that sheet that I gave you and go to the ratio test and write factorials, right? In a little box right under the ratio test, write factorials, so n factorial, so you know, right, when you are learning and studying this sheet. Now, I did tell you this before. You have to memorize all of these tests, otherwise you'll just be, staring at this stuff. And for many years, as students are taking the test 3, what I find is actually when I flip the test and look at the back page, you guys reconstruct the entire sheet on the back and then have it as a cheat sheet, right? So students will be kind of working on this sheet and memorizing the sheet, and then you just recreate this sheet at the back of the test, and then you go through it. All right, so problem 16. Well, that was really easy because, right, we had n factorial gives us the ratio test. We use the ratio test immediately. Let's pick another one from this group, and then we'll move to the next group. Problem 14. Oh, beautiful. Look at that. Problem 14. A whole mess of 7n squared minus n minus 2, and then we have 4n to the 4 minus 3n plus 1 from 1 to infinity. This is a great problem to talk about. Divergence test? Nope, right? Not working here because you have n squared or k squared divided by k to the 4th. The limit is 0, so test is inconclusive. So we have to look at which of the 9 tests we are to use here. Let's go to the list that I gave you. Does this look like geometric? Is it exponential? No. Strike it down. Does it look like p-series? Ah, p-series deals with polynomials. And these are polynomials, right? This is how you immediately know that, I have something that is polynomial divided polynomial. P-series deal with that, so I have to use a comparison to P-series. Use the comparison to 1 over k squared, 1 over n squared. So compare it to this. Well, actually, it's not going to be 1 over. It's going to be 7 over 4 n squared. So P-series, it's not a P-series, but it looks so damn close, right? It doesn't have minus 1 to the n. It's not alternating. It doesn't have, right? You're not going to use root and ratio. None of that stuff works, right? You can't integrate this. It's just terrible, right? So pretty much everything else falls off the truck. Compare it to Bn equals 7 divided by 4n squared. So compare it to Bn, writing it down, compare it to 7 divided by 4n squared. And that's going to be convergent by P-series. So in the limit test, limit comparison test, they should converge. This problem should converge. Obviously, learn how to do these problems. Let's take a look at the other column over here. Lots and lots of cool problems. Pick something else. Now we're looking at 23 to 36. Great. Summation 1 to infinity, negative 1 to the n plus 1, 2n plus 1, divided by n factorial. Talk to me. What is the obvious feature? The alternating, right? The problem can be solved by ratio test like this, because ratio test has those absolute values that would kill this negative 1 to the n, right? But we don't have to go extreme. We can immediately recognize that there is minus 1 to the n. I don't care, n plus 1, n minus 3, it doesn't matter. It's just negative 1 to the n of some sort. And we know it's alternating series. So your job now is to show it's decreasing and the limit is 0, which both is. So it goes on a convergent. And then you are going to have, like we did yesterday, the series of only an term. Now that's going to be a ratio test, right? That's going to be a ratio test. So this one should work out to be absolute convergent by alternating through ratio, right? So alternating series plus ratio, and that would get you. Yesterday, we talked about alternating series test, and we learned that you have that procedure. So take a look at the video one more time to make sure that you have the procedure down. You go and figure out decreasing, so figure out AN, figure out decreasing, and limit is 0. And then you are on convergence branch, and then summation of AN without alternating term, that converges or diverges, which leads into absolute or conditional convergence. So that's that. Okay, what else? Pick another one from this list. We already talked about 30. What's 30? I just mentioned it literally 5 minutes ago. No, number 30. Integral test. Now it's going to be pain in the neck integral test there, but yeah. There's going to be some parts and so on. But you can also do a comparison test. You can do the comparison on it, sure. 30 can be done either way. All right, what else?
26.
26. Oh, 26. That's a troll question for the exam. 5 plus sine k divided by root k. N, whatever, m, whatever. Oh, that's a troll question. So what do we know about sine and cosine when we are talking about series? We can ignore them. Why? It's beautiful. Sine k at most is going to be 1. Cosine k as well, at most is going to be 1. So that numerator there is at least 5, at most 6. That has no way on convergence or divergence of the series, right? So sine k can be, well, it could be -1 as well. So the numerator here can be anywhere from -1 to 1, so from 4 to 6. That's not going to change anything with infinitely many terms, right? So you can, for all purposes, just erase sine k from this problem. Great. So now you are looking at 5 divided by root k. Now what's that? P series. It's k to the half. And what do we know about the half? Is less than 1, and if it's less than 1, P series diverges. Good. So diverges by comparison to P series of 1 over k to the half. You can do direct, you can do the limit comparison. It is going to diverge on this problem because the P series. Now, if the square root k was k squared, what happens then? If root k is k squared, what happens then? It's the same problem. Yeah, converges because now P series is P is bigger than 1, right? So just by this, the convergence of this problem depends on literally on the denominator k. What is the exponent of k? 1/2, diverge. If it's just k, 1, diverge. If it's anything bigger than 1, converge. So this is going to be comparison to P series, and it's going to diverge. Good. So we did 3 from there. Let's take a look at this stretch of problems here. Let me ask you about 39, since it's so nice and busy. What do we use? Ratio test. There are factorials everywhere, right? So no thinking about it, just fire up ratio test and move along. Do we have any scary stuff over here? Problem 42 is interesting because problem 42, and you need to write this one down, guys. This is actually two separate series mushed into a one series. You can break this fraction because you have addition in the numerator. You can break into two fractions, and then each one gets its own series. So this is actually two separate problems that are in a single one, and I can see this being an issue, right, for some not to see something like this. So you have your summation 1 to infinity of 2 plus negative 1 to the n divided by 2 to the n. This breaks into 2 over 2 to the n, 1 to infinity, plus summation of negative 1 to the n over 2 to the n, 1 to infinity. And you are looking at two separate geometric series. So it splits in the numerator. You can do that in the denominator, obviously, but you can for the numerator. So it splits into two, and then you get problem 44. It's a comparison, right? Look at the exponent on k. Exponent on k is going to be 3/2, right? No, it's not 3k, it's k. K times k is k squared. Square root of k squared is k. So this one gets compared to 1 over k to harmonic and should diverge. 44. I said should because I haven't done the problem. I was just looking at it, knowing what to do. K times k is k squared. Square root of k squared is just k. So this problem, when you delete the noise, which is that minus 9, when you delete the noise, it just becomes k squared. Square root of k squared is k, 1 over k. 1 over k, that's going to be harmonic, divergent. So we are expecting this one to diverge in comparison to 1 over k. So 44 should be compared to 1 over k. Good. 47, factorials again. And now I would like you guys to work and try and figure out problem 48. So this is going to be a problem that we are going to work out fully. We haven't done any of the problems like this before. So you are given 2/3 plus 3/8 plus 4/15 plus 5/24 plus 6/35 plus ... Your job is to figure out the formula from whatever to infinity and use appropriate tests to say whether it converges or diverges. That would be the last problem for tonight. So let's see what you guys, for this, and then we'll take a break. When we come back, we'll do first out of 4 sections of power series. All right. Do you have the formula that would generate these terms?
N equals 2.
So it will start with 2, okay, to infinity.
It'll be N over
N over, I like it,
N squared minus 1.
N squared minus 1. Excellent. Excellent. If you take a look at the bottoms, you have a 3, which is 1 less than 4. 4 is a perfect square. You have 8, which is 1 less than 9, which is a perfect square. 15 is 1 less than 16, and perfect square. So if you take a look at this, you have 2 squared is 4, 3 squared is 9, 16, 25, 36, and all of these numbers are 1 less than this. This one is 2 squared minus 1, 3 squared minus 1, 4 squared minus 1, so n squared minus 1. So looking at the patterns to determine the formula. So now I have the formula. That was really good. And does this converge or diverge? Which test do I use? Well, it's going to give us inconclusive on the divergence. Remember, we try divergence first. And we're going to get 0 there. So that's useless now. We are going to have n divided by n squared. What do I do with that? Yes?
Compared to 1 over N.
Excellent. Compared to 1 over n. Because in a great scheme of things, when you take the noise away, you have n divided by n squared, which cancels down to 1 over n. So this problem should diverge by comparison to 1 over n. Okay, let's say that our Bn is 1 over n. Summation of Bn diverges by P series or integral test, whatever. So now we can do the limit comparison. N goes to infinity of an, which is the original problem, divided by what we are comparing to. We get the limit, n goes to infinity, and then we have n squared divided by n squared minus 1, which is equal to 1. And that is L, it's finite. The other one diverged, so they share the same fate. So answer, since summation of Bn diverges and the limit an over Bn is equal to 1, series, and now you have this whole spiel of 2/3 plus 3 over 8 plus 4 over 15 plus diverges by limit comparison test. This red sentence is not optional, guys. We talked about it yesterday. We said this is the answer to your question. This carries points. Now it's perfect to practice that in MyMathLab because they have it there. You lived through the chapter on sequences and series. The next chapter, chapter 11, is on power series, right after these messages.